Welcome everybody. Welcome to this new Discover Us webinar from the webinar series. You know that every month we take the opportunity to organize this webinar to present to share with the community the project objectives and to have a relevant presentation of the people participating in Discover Us. So today we have Germán Moltó from the Universitat Politènica of València. Germán is a full professor at the UPV. He specialized in distributed computing, cloud computing, and now serverless computing. He has a strong background in middleware technology, orchestration, cloud, etc. He has participated and contributed to many European project and is contributed to many European infrastructure. The last one, the European Open Science Cloud, EOSC, participating in different projects as Synergy, EOSC Synergy, EOSC Beyond, the EOSC Hub. And in particular is the team where Germán works is responsible for open source developments in the field of cloud orchestration. So today he will present the deployment execution of applications along the computing continuum using the tools developed by UPV, namely Infrastructure Manager and TOSCA. So Germán has also been visiting Argonne this spring, so it's part of this program of Discover Us. So please, Germán, thank you for being here, and we are happy to hear the latest development from your team.
Thank you very much, Daniel, for the nice.
If you have any question, you can have at the end. You can write in the chat. We will take and we'll discuss at the end. Thank you.
Thank you very much, Daniel, for the nice introduction. So let's get right into it. So as Daniel was mentioning, I'm from the GRICAP Research Group as part of the Institute for Instrumentation of Molecular Imaging Technologies at UPV. So we are working on middleware for cloud infrastructures. And in this talk, I'm going to focus on the developments that we have been done in the context of the projects that we are involved. And this is, as always, a joint work from many of our colleagues. Our research group is led by Ignacio Blanquer, and this is the main status of our research group at the moment. Now, as you know, we are in this situation in which computing takes place at different layers, in which this is called the computing continuum. And we find layers closer to where data is produced and layers where more computing power is available. And there's a wide spectrum and myriad of infrastructures. From edge computing to fog computing, HPC or on-premises computing, infrastructure as a service, cloud computing, and function as a service, serverless computing, and also data lake technologies that provide the storage substrate to mid-term and long-term. And mainly our work in this, my focus in this talk is to describe some innovative open source services that we have developed in our research team and that we have been integrating in the last European projects in which we are participating, mainly in the area of deployment and execution of applications on the computing continuum. This talk is going to focus on Infrastructure Manager and Oscar, but we also take an opportunity to say a few words about these other developments that are a part of the ecosystem of these two technologies. And the main focus is infrastructure provision. We need to deploy virtual machines, we need to deploy containers, then we need to deploy applications on top, and then we need to do services orchestration on top. So this is going to be the main focus of this talk. And I will start with the Infrastructure Manager. The Infrastructure Manager is the flagship development from our research group. This is an open source tool, and it's also offered as a publicly available production service that allows to deploy customized complex infrastructure across multiple cloud backends. So whenever you want to deploy, let's say, a cluster for computing or a Kubernetes cluster or a Spark cluster or a Storm cluster, then you can use this TOSCA standard to describe your application topology in terms of the number of virtual machines, in terms of the underlying operating system, the applications that need to be installed, and this is included in a description, and this is a trend called infrastructure as code, and these templates can be stored in your GitHub repository, for example. And then the infrastructure manager is in charge of deploying these resources from this TOSCA-based specification. And the nice thing is that TOSCA is a standard, so you can replace the infrastructure manager with another TOSCA runtime to do the deployment. So the infrastructure manager automates the provisioning, configuration, installation, monitoring, and update of this virtual infrastructure. Now, it's using these DevOps capabilities. It's using Ansible under the hood. Ansible is a DevOps tool that allows to not only interact with different cloud backends, but also to provide some recipes in order to install software on top of the virtual machines that have been provisioned. The IAM plays nice with other open technologies such as REST APIs, XML RPC APIs. It provides command line application, a web-based dashboard. It's distributed under an open source license, and it's available on GitHub. Now, the infrastructure manager supports many different cloud backends. It's using under the hood a library called Apache Lead Cloud to interact with different cloud backends. And when there is no support in this library, it interacts with the specific APIs from the underlying cloud. And it supports the major hyperscalers such as AWS, Google Cloud Platform, Microsoft Azure, but also European infrastructure as a service clouds. We're talking here about the Systems Open Telecom Cloud, Cloud and Heat, Orange Cloud. So this is why this technology, we have been using it in several European projects as the substrate or the technology used to deploy virtual machines across multiple clouds. Supports many on-premises cloud management platforms. We're talking OpenStack, OpenNebula, VMware as well. Also federated platforms, CGI Cloud Compute, also Chameleon, as I will describe later, a testbed from the US. And it can also deploy on a managed Kubernetes platform. And this list can easily extend it by plugins. So it also provides a REST API. It's very convenient because the infrastructure manager server can be integrated with other services that act as third-party clients to the infrastructure manager. So whenever you need to do infrastructure provision across multiple clouds, then you can use the infrastructure manager to do this, following the Open API specification. But the main let's say entry point to the infrastructure manager is this IAM dashboard, which provides the entire lifecycle management of virtual infrastructure. So this is aimed at non-advanced users, so you can easily deploy infrastructures from your web browser. And here what we provide is a curated set of TOSCA templates, but the users do not need to understand what TOSCA is. And we provide templates for deploying Slarm clusters, Storm clusters, Argo workflow, Kubernetes clusters, you name it. There's a whole catalog of TOSCA templates that have been curated, and under the hood we're providing Ansible roles, which is the technology used to deploy or to configure these clusters on the provision virtual machines from the underlying cloud. And this dashboard provides the ability to see or to manage the life cycle of this virtual infrastructure. So you see that this deployment in OpenNebula, this one in OpenStack, this one in the AGI federated cloud, this another one in OpenStack, and you have this ability to manage your infrastructure. As I was mentioning, UPV is operating a publicly available IAM service. This is offered as part of the EGI catalog of services for research. And EGI is the largest federated infrastructure for scientific research in Europe. I will have a brief words in the next slide. And we are offering this service as TRL 8.9, the technology readiness level, so it's production ready to be integrated. So now that I mentioned EGI, the EGI Federation, this is a European flagship digital infrastructure for data-intensive scientific computing. It supports more than 100,000 users, more than 62 million cloud CPU hours consumed in the last year, being involved in 32 European Union funded projects, and it's an enabler of computing power and storage capacity for researchers in Europe. And this is a federated infrastructure, the largest federated infrastructure that we have in Europe, and it provides a set of AGI services for research, for the deployment of virtual machines, cloud container compute, and here you see the infrastructure manager offered as part of the catalog of services. Here are a couple of screenshots. Perhaps the most popular one is to deploy a Kubernetes cluster. And once you select a Kubernetes cluster, then you can further customize it with additional software on top. But you see that it supports lots of popular computing platforms such as HT Condor, Slurm virtual clusters, Hadoop clusters. And for example, if you select a Kubernetes cluster, then you can further configure to deploy, for example, Jupyter Hub to deploy Jupyter notebooks on top of Kubernetes, or deploy a secrets management system on top, or Apache NiFi to create data processing pipelines, or Prometheus to gather metrics, or Flink for data processing. So you see it's quite a flexible platform that offers curated set of Tosca templates for the end users. And I'm saying that these are created Tosca templates because there are periodic security assessments done using popular open source developments to understand whether the software that is deployed there doesn't expose any known vulnerabilities. So this involves a periodic assessment of this Tosca template. Now, the infrastructure manager architecture, you will see that the IAM server, this is like a client-server architecture. So the dashboard is just a client for the server through the REST API, and the command line interface is also a server for the REST API. This is integrated with the HashiCorp Vault secrets management system. So anyone can use the infrastructure manager, and if you don't trust our service, you can just pass a reference to your vault so that we can fetch in a secure manner temporary tokens to deploy the applications on your favorite cloud on behalf of the user credentials. And we have been extending the infrastructure manager in the last years to not only support elasticity frameworks such as Clues, because we are able to deploy elastic virtual clusters that can grow and shrink in terms of the number of nodes, but also extending it to deploy applications along the computing continuum. So we can, from the Tosca specification, we can deploy functions on AWS Lambda, for example, which is a serverless offering from Amazon Web Services. We can deploy on federated on-premises cloud, but we can also deploy it on low-power devices using another technology that we have been developing, which I will talk about later, which is called Oscar, running on minified Kubernetes clusters. So basically, the infrastructure manager is a flexible technology into that. So I will not play this video, but I will provide the slides, and then you can see a summary of this, how this technology is used. Now, the infrastructure manager is being supporting several scientific communities in the last decade. For example, related to the infrastructure manager, there is the Pangeo, related to geophysics, and also the Earth Network for European Network for Earth System Modeling, which are using the infrastructure manager to deploy all their computing capacities to run Jupyter Hub and also these data cube processing tools. And thanks to the infrastructure manager, these are dynamically deployed, they spawn on the AGI federated cloud, they do the analysis there, and then they destroy the computing infrastructure. So it's a flexible tool to do this. Now, the infrastructure manager has also been used, for example, in the ASprint project, which finished last year, to deploy all the computing infrastructure required for training and for inference, and also for the monitoring of models. In the DTGO project, which is still active, finishing this summer, the infrastructure manager is used to deploy these customized Slurm-based clusters, and you know that the Slurm is the most popular batch system used for supercomputers, so that scientists can train their computing skills in these virtual clusters using similar execution frameworks that they will find in supercomputers, and before moving on to these, let's say, expensive hours that are provided by the supercomputers. In the InterTwin project, which is still active, the IAM is being used to deploy all the virtualized infrastructure to perform real-time data ingestion and deploy all the engines required to support digital twins. We're talking about Kafka, for data ingestion, Airflow for workflow management, MLflow, YPro for data provenance, Horobot, Galaxy for bioinformatics application. So basically, we produce a set of Tosca templates and integrate them into the dashboard. And the digital twin users can easily mix and match in order to deploy their digital twin engine from the convenience of their browser. In AI4EOS, the infrastructure manager is being used to deploy models from the AI4EOS marketplace in multiple platforms. So these are pre-trained AI models. So basically, you have the Docker image with all the models weights inside. And with the infrastructure manager, you can deploy a virtual machine customized with the runtime environment required. And you can deploy it in AWS, Azure, Google Cloud, OpenStack, even in the EOS node, as I will mention later. And also supporting all the infrastructure for training, which in this project, instead of using Kubernetes, we are using Nomad, which is also a very nice technology with a low, let's say, learning curve compared to Kubernetes. And the infrastructure manager is also the deployment service of the execution framework as part of the EOSC Beyond project. EOSC is the acronym of European Open Science Cloud. This is a flagship initiative from the European Commission to create this web fair of data, and data needs also to be processed. And we are using this technology to not only deploy the virtual infrastructure required for data processing, but also to create connectors to automatically fetch the data set from open data repositories, let's say Zenodo, for example, in order to ingest this data into the dynamically provisioned virtual machines, and also to move the data from the open data repositories close to where computing will take place. We are using the EOSC data transfer service for that. Now, the infrastructure manager is also the application management layer of this application workflow management service provided by the EOSC EU node procurement. This is not a research project. This is a procurement action from the European Commission, which operates in production the first node of this EOSC federation. So basically, we are operating the infrastructure manager there in production until 2027. And if there is an extension, we will continue its operation with, let's say, very extensive security procedures and management supervised by the European Commission itself. And as I was mentioning, the EU node is the flagship initiative from the European Commission to create this platform to facilitate access to computing, storage, and data transfer service, among other, to European researchers. So any European researcher at the moment can get a certain number of credits to do computing on the EOSC EU node. This is a production platform available at this URL. And what kind of services you have access to as a European researcher? You have access to OpenStack and OKD platforms to deploy respectively VMs and containers. We provide this curated tools catalog that are deployed using the infrastructure manager. There are data transfer service, managed Jupyter notebooks. So it's quite a convenient platform, I would say, for this long tail of science for researchers that do not have access to computing capabilities. They can directly go to the EOSC EU node, log in through their University of Research Center credentials, and automatically get assigned credits to do computing there. So keep in mind if you are a European researcher. There was, as I was mentioning, the IAM is openly available. There is no need to register. You can go right now to this URL and you can log in through your university or research center credentials. There is no need that you are a European researcher. I mean, the European researcher is for the EOSC EU node, but the IAM is openly available to anyone. So I encourage you to take a look if you want to further experiment with this technology. And there was this opportunity that came to integrate with other federated cloud infrastructure across the Atlantic. And here we focus on Chameleon. Chameleon is a configurable experimental testbed for this edge-to-cloud research. It's being managed by the University of Chicago and our National Lab. And during this vision workshop that the Discovery as initiative organized in Savaldia on June 2024, there was this meeting with Kate Cahey, and there was this discussion on the lack of transatlantic computational testbed across both sides of the Atlantic. So there was this call of research exchanges, and as Daniela was anticipating, I did a research exchange last April at our National Lab with the goal of integrating the infrastructure manager with Chameleon Cloud. The title was Dynamic Deployment of Transatlantic Computational Testbeds via the Infrastructure Manager. So as you know, the Discover Ask has several topics or priority topics. This one was related to managing complexity through high levels of abstraction. And the goal here was integrating Chameleon as an additional cloud backend in the Infrastructure Manager, with the goal of creating computational testbed that span across both sides of the Atlantic. So even if this involving EGI, Federated Cloud, and Chameleon, both are separated entities and both are federated, but there is no single federation among them. So having the Infrastructure Manager to be able to deploy a unique computational testbed across both sides that are not federated, I think this is valuable technology because there is no need to have a common federation and common authentication and authorization system under the hood. We can federate at the level of the deployment of infrastructure. And we wanted here to focus on this other technology, which is called OSCAR. We wanted to deploy computational testbeds with separate OSCAR clusters across both sides of the Atlantic. And OSCAR is an open source serverless platform, serverless in the sense of event-driven and scalable platform for data processing applications that run on elastic Kubernetes clusters. So these clusters are deployed through the Infrastructure Manager and can grow and shrink in terms of the number of nodes that are being executed there. So we are able to deploy OSCAR on any of the cloud platforms that the Infrastructure Manager supports. And it also runs on ARM-based low-power devices. And we have been using this technology mainly to run AI inference of pre-trained models in several projects, say Sprint, AF4EOSC, Imagine, and Intertwin. And we have been also integrating this technology with AWS Lambda to run workflows along the competing continuum. So here, basically, the idea is that users upload files to this object storage system, and this triggers execution of jobs that run on this scalable Kubernetes cluster. And you can also run services that are exposed outside of the cluster. You can also trigger them through REST APIs. And the output data is stored in one of these object storage systems. Dcache, OneData are scientific storage systems. Amazon S3, an offering from AWS, and MinIO provides an API compatible with Amazon S3. This can run anywhere. So basically, OSCAR services are based on Docker containers. So we were encapsulating a Docker container, in this case, the model weights and the runtime environment to run the AI models. So when users upload files, for example, an image to be processed, this triggers the OSCAR service that run, for example, YOLO V8 to do object detection there. And this runs on pods in the Kubernetes cluster. Now, we have been using these technologies I was mentioning to run workflows along the computing continuum. And here, for example, we have a cluster of Raspberry Pis, which we are running with a minified Kubernetes distribution, which is called K3S. So we capture some images. We anonymize these images close to where data is captured. And once the images are anonymized, then it's uploaded to an OSCAR cluster running in the EGI Federated Cloud in order to perform the face detection on these anonymized images. And the data is stored in a data lake technology called OneData in the EGI Federated Cloud. So it's quite flexible technology that can run on several computing platforms. But we have been exploiting this technology in two projects. AI4EOSC focuses on the European Open Science Cloud and provides a platform to train and perform the inference of models. And we are deploying production OSCAR clusters, whether users are deploying their AI models for inference. So this is part of the AI4OS software stack, which this is a very comprehensive platform for a training and AI model. And this platform, which is being developed in this project, is being exploited in production in this other project, which is called Imagine. And Imagine is an AI European project focused on aquatic data sciences. And there is this very nice use case from the EMSO OPSI Underwater Observatory, in this coast of Spain, in which they have these underwater cameras that take periodic pictures of the fauna, and they need to identify the species, and they need to understand the impact of the different seasons on the population of the fishes, and also the impact on climate change. So they have these historic images, and they need to analyze and also perform real-time object detection or fish detection in this activity. So for this collaboration between UPV and Argonne, in order to create this computational testbed, we use the infrastructure manager to deploy these two OSCAR clusters, one in the LIP center at Portugal as part of the AGI federated cloud, and the other OSCAR cluster, remember that these are Kubernetes clusters, were deployed at the Texas Advanced Computing Center as part of Chameleon Cloud. They were easily deployed through the infrastructure manager. We just needed to do an integration with the Blazar reservation system that Argonne had initially conceived for themselves, but they later contributed this upstream to the OpenStack project. And we contributed upstream to the Apache libcloud library, the support for the Blazar reservation system. So this is also a nice contribution that we perform for the scientific community in this state. And here we have a couple of OSCAR clusters. This one in the US, and this is running in the EU as part of the AGI federated cloud. So basically, users upload files to this MinIO bucket, and then this triggers the execution of jobs for performing this fish detection. This cluster is scalable; it can grow and shrink. And once this cluster is overloaded, it can delegate some jobs to be executed in this cluster in the US, which again, this cluster can be made elastic to grow and shrink. So here we have a computational elastic testbed, transatlantic, that can adapt to the underlying workload being executed for the scalable execution of AI model inference of fish detection. And I think this is a very nice use case that was, I would say, quite straightforward to assemble using the infrastructure manager for deployment and OSCAR for the execution. There was also another use case that we were tackling. This was mainly led by my colleague Estivalit from a research group in collaboration with the Deltares. This is a Dutch institute that focus on flood assessment, especially the effect of flash floods in urban areas. And this is being done in the context of the InterTwin project, which is creating this digital twin engine platform. And sadly, our city suffered last October. Valencia suffered this major flash flood, in which on this date, it received a year's worth of rain in just 8 hours. So basically, this caused devastating flash floods, turning streets into river, and more than 220 people died, more than 140,000 cars devastated. Still several towns, I would say, more or less affected, and people still recovering their lives. So there was let's say, a use case that was, let's say, that affected us in some extent. And we take a look at these images from the satellite. Here is the coast of Valencia. This is the Albufera Lagoon. If we take a look on the 30th of October, we see all this area flooded with some major cities and towns in the southern part of Valencia, which were completely flooded. And actually, this is the footage that I took from the airplane on the next day. And you will see completely this river that was flooded, and also this area. These were dramatic images. And let's hope it doesn't happen again. So now for this use case, in collaboration with the Deltares, we focus on the very same underlying technology, these two OSCAR clusters deployed across both sides of the Atlantic. And in this case, here, there are some Jupyter notebooks that are creating this configuration of the workflows that need to be executed. This is using the common workflow language specification under the hood for orchestrating the different steps of the workflow. And the idea is that several steps of the workflow are, I mean, they are orchestrated centrally, but some of the steps of the workflow are offloaded into different clusters in order to take advantage of the increased computational power that we can gain from this federated infrastructure, in which we can deploy access to GPUs, for example, if we do have access to them, and also deploy additional computing capacity that we may not have within our research institution. So the common workflow language is being orchestrated, and some of the steps of the workflow are being offloaded into these separate clusters. And I would say this is also a very nice use case that was successfully executed in this research exchange. Now, another topic that we have been tackling regarding the execution in the computing continuum is the connection to HPC. As you know, cloud systems and HPC are totally different entities with different technologies, different approaches, different authorization and authentication mechanisms. And in the context of the InterTwin project, there is this very nice technology developed by the Italian Institute for Nuclear Physics, INFN. This is called Interlink, and Interlink provides this virtual kubelet approach in which, as part of a Kubernetes cluster, and here I'm representing an Oscar cluster, which you remember it is a Kubernetes cluster, you can add an additional node represented as a virtual kubelet. And when a pod is scheduled to this virtual kubelet, this is offloaded through this Interlink software into an HPC supercomputer. In this case, we established a collaboration with the ISUM Center in Slovenia, and this is the HPC Vega supercomputer as part of the Euro HPC. So the idea is that we connect all the different pieces, and from the point of view of the scientist, the scientist uploads file to an object storage system. In this case, we're using dcache, but it's just uploading a file. This file, uploading the file, triggers an event, and this event is captured in Apache NiFi. Apache NiFi is collecting several of these events, and is scheduling a job into Oscar, and then this job is being delegated into an HPC supercomputer, because the HPC has lots of GPUs available. So it's a way of integrating HPC into the cloud computing world, and the output is stored back into the cache. So from the point of view of the user, is I upload a file, I wait, and the result appears magically in another folder from this object storage system. And I think this is a very nice integration in which we managed to perform this integration. And we made a joint collaboration between CERN, which is the development of this iTwin AI library, UPV, and INFN, which are the developers of this technology. Now you see here this iOS tool. This is also an open source development that we contributed. So we are using this technology to integrate support for additional sources of events. So one uploads files to the cache, we receive an event here. One sends a message to Kafka, we receive an event here. So we are providing several sources of events. And you saw in the very beginning this mention to data lakes, and data lakes are gaining lots of relevance, and also in the area of data spaces. And Rusio is one of these technologies that provides data lake management. And in the InterTwin project, there is this federated data lake managed by Rusio. Rusio provides the ability to define rules to distribute data across multiple sites across Europe, for example. And we integrated Rusio support in Oscar, so that one uploads files to Rusio, these are computed in Oscar, and also using Rusio as the storage backend for the output of the Oscar execution. So we are kind of expanding the integration across our technologies. Now, let me just spend this last few minutes from the presentation to just mention a couple of other technologies that we are using related to infrastructure manager and also Oscar. This is a topic of reproducible computing, which is, is a major topic. And here what we wanted to contribute is with a library for reproducible computing of computational experiments that require complex computing infrastructure. So the idea is that you have in your Jupyter notebook the description of your computational experiment, but you can also couple your Tosca template that deploys the precise configuration you require to reproduce these computational steps. For example, let's say that you need an Slurm-based cluster with 5 nodes with this specific software package. This is described as a Tosca template that you embed in your reproducible package. So you can use the infrastructure manager from Jupyter Notebook. So the Jupyter Notebook acts as a client of the infrastructure manager for deploying the infrastructure required to reproduce a computational experiment. And we contributed this back into Chameleon as a trophy reproducible artifact. So that any Chameleon user can also use the infrastructure manager to deploy even on Chameleon. So it's, as I was mentioning, it's quite flexible technology because we can, from the perspective of the EGI, we're contributing a service that even users from the US can use our service to deploy on the infrastructure on the US. So it's quite flexible technology. And let me just spend a few minutes talking about this AI for Compose. This is also a tool that we have been exploiting in a couple of projects in which we allow the visual composition of AI inference pipelines. The goal here is to provide the user with a drag and drop composition. And we are using Oscar under the hood. And once we have deployed the AI models in Oscar, and remember that these Oscar clusters can run on different layers of the computing continuum. We can run it on a cluster of Raspberry Pis. We can run it on AWS or on the EGI Fidelity Cloud. So the user can compose a pipeline, and each one of these steps can run on separate Oscar clusters. So here you're composing a workflow that in the end is orchestrating from this entity, but it's offloading the execution across several clusters. And here we're using a couple of technologies. This Node-RED graphical composition tool based on Node.js, and this Elira tool based on Python, which we contributed its supports in the EGI Notebooks tool. So any EGI user can use Elira to compose AI inference pipelines that run on Oscar clusters. So again, we are expanding, let's say, our ecosystem of tools, trying to integrate with other tools from the European Open Science Cloud, let's say Realm, and outside of this. Here you have an example of this inference pipeline. So you load an image, you pass it through a Grapefy service. This can run on a separate Oscar cluster. Then you run another plant species classifier, which can run on another cluster, and then you issue the results. So this is typically a tool for end users. We don't want to spend time messing with YAML files, deployments, just a drag and drop approach to the composition. Now, this webinar was scheduled to last for 45 minutes, so we still have a couple of minutes left. So let me just jump to the conclusions and key takeaways. I presented the Infrastructure Manager, an open source tool and a production service that can be used as a federating component to deploy computational testbed that span across multiple cloud sites and also layers of the continuum. I introduced Oscar to support this serverless event-driven execution of applications in the computing continuum. It can also offload to HPC supercomputers via interlink, so we cover several layers there. I briefly mentioned Apricot Lab to facilitate deploying these testbeds required to reproduce computational experiments on clouds. And finally, I described briefly AI for Compose to visually design these AI inference pipelines that execute models applications that can run in remote Oscar clusters. And with this, I think this is all. These are the acknowledgements. First one for the Discover Us for funding the research exchange. Also part of these results were using the Chameleon testbed and some projects such as AI for EOS, Imagine, and Intertwin, which were involved in this project. Now, if you have any questions, I will be very happy to answer them. Thank you very much for your attention.
Thank you, Germán. Very interesting developments. So yeah, we can go now to the questions. So there is one. So it's regarding Intertwin and the connection with HPC systems. Do you handle time-constrained workflows considering the batch nature of HPC queuing and the potential delays it may cause. So it's about how do you integrate with the HPC.
Yeah, exactly. That's a very good question, Eduardo. Now, the goal here, no, the goal here is that if we take a look at this, at this diagram, basically here one job being executed here is the execution of a single inference. Let's say, for example, on an image, you receive an image and then you execute a pre-trained AI model to the inference phase on this specific image. In this case, it was an image where we were using the 3D GAN generative adversarial network on a use case coming from CERN. But the idea is that we are not executing here in HPC an entire workflow. This single, let's say, pod that would execute here is translated into a single Slarm job that is executed here as an apptainer application enqueued in the Slarm batch system in HPC Vega. I mean, nothing prevents that in this Slarm job, as part of the steps of this Slarm job, you execute a workflow of several steps. But this will be confined on the runtime environment allocated to this single job running in the Slarm. Did I answer your question? If not, please feel free to ask again and I will polish my answer.
Okay, thanks for the answer. So Ken is asking, the applications you demonstrate are impressive. Are there any security reliability challenges that follow from the quite large attack surface complexity?
Very nice, very interesting question. I mean, here we focus on, let's say, proof of concept integration. But if we take a look at the testbed, for example, spanning across the two sites, for example, here what we have is we have a Kubernetes cluster that is exposed using OpenID Connect authentication or basic auth authentication. And here the same approach, OpenID Connect authentication or basic auth authentication. So the only two services that are exposed to the outside world are the API of OSCAR, which is not open. You need basic auth or OpenID Connect authentication through JSON Web Tokens, and MinIO. And MinIO is also exposed through TLS, HTTPS, as this API. And also you need to authenticate through MinIO. I mean, there are no open services, and the only two entry points are these two. So unless there is a unknown 0-day in Kubernetes, I mean, things are, I would say, quite protected. Because everything that happens inside, there is no, let's say, inbound connectivity to all these components. The only two entry points are these ones and this one.
Okay. Another question again from Eduardo. So again, connected to the previous question, he was not worried about the use of complete workflows in Slarm, but more about how do you handle inference evaluation that are urgent, while Slarm cannot guarantee that the result will be available when you need. So
Yes.
that Eduardo is asking maybe if you interact with the policies of Slarm, or how can you guarantee?
Yeah, that's a very good question. No, the thing, I mean, in Slarm, you can create different queues. And I understand that in Slarm, these queues can have several priorities. So again, if we go to the diagram, let's see over here. Sorry, because it's taking a while to load. If we see here, the interlink has like two pieces. One server side that the HPC admin needs to install in the front-end node of the cluster. And the other part is the virtual kubelet, which needs to be installed in Kubernetes. So the sysadmin of the HPC system needs to configure interlink to specify the queue that will be used for offloading. So there needs to be, let's say, a connection between this virtual kubelet and the specific queue of Slurm configured by the system administrator. So basically, in our case, we were more interested in the technical interoperability rather than on achieving close to real-time inference, because of course, in Slurm, when you submit, it's like kind of submit and forget. And when you have the resources available, these are allocated to the job. So there are no preemptive policies that are put in place, but they understand that creating a specific high priority queue in Slurm and linking it to interlink, that could do the trick.
Okay. So next question is about how you achieve the provisioning, the scalability of provisioning. So how you shrink and grow inside the deployment.
Very nice. Yes, if we go here, for example, in the first slide about Oscar. Yeah, here. For example, you see here this clues component. This is an elasticity management system that we developed in our research group. I mean, like a decade ago, and we have been extending it with different plugins. So basically, these clues contacts with the different batch systems. If we are in a Slurm cluster, it queries a Slurm. If we're in a Kubernetes cluster, it queries the job management system of Kubernetes. And this elasticity system basically has a certain policies, and depending on the number of queued jobs and depending on the amount of time that these jobs have been queued up, and the elasticity, let's say, quotas, I mean, the maximum number of nodes and the minimum number of nodes, it decides to deploy these new virtual machines or terminate them. And clues interacts with the infrastructure manager. So the idea is that if the cluster needs to grow, this component talks to the infrastructure manager. It just issues an operation to add a new virtual machine, and this virtual machine is automatically integrated with Kubernetes. And if you need to remove a virtual machine, you basically this activates the drain system of Kubernetes. It removes all the pods and then it terminates the virtual machine. So the logic is done here in this clues elasticity system, which is also an open source development from our research group.
By the way, staying in the question, staying in the elasticity part connected with the previous question about HPC. Did you try some Slurm elasticity features in some HPC cluster or not? You know, the Slurm
well, I mean, the infrastructure manager can deploy Slurm-based clusters, but these are virtual clusters.
Yeah.
These virtual clusters running on the cloud, this can be elastic.
Yeah.
But these are on the virtual clusters.
Okay. Okay.
I have one, Daniele, if you want. Yeah, thank you, Germán, for the talk. So you have done this integration with Chameleon Cloud, and my question is about adoption. Do you think they are going to adopt your components in Chameleon or in general in the States? What is your feeling?
That's a very good question. I mean, I would say it's not the best geopolitical climate at the moment for this kind of cooperations. The technical integration is there, and currently at the moment, anyone, I mean, the technical achievement is already there. Any Chameleon user can log in into the infrastructure manager. It can put the application credential from the Chameleon cloud in the infrastructure manager and do the deployment. So this is already there. If I think that Chameleon users will adopt this technology, I'm not sure about that unless there is a specific push or train for the users, because the users will not know how to use this technology unless they are trained that this exists. But I think this is flexible enough, and I think this work also paves the way to integrate with other federated infrastructures. And we will be happy to undertake this work with other federated testbeds that are available there. And let's see, I think we did our part, and we are pushing for this memorandum of understanding between Chameleon, EGI, and EPB. Let's see how it goes.
Okay, thank you very much.
Okay,
Thank you,
so
Rachel.
very last comment, I think, again from Xavi from the previous question. What are the KPIs to grow or shrink? Do you have some KPI implemented?
By KPI, I mean, you mean the elasticity rules? The elasticity rules are typically, I mean, it really depends if it's a Spark cluster, Hadoop cluster, a Slurm cluster, or Kubernetes cluster. But mainly for Kubernetes are the number of pending bad jobs in the Kubernetes scheduler. And this is configurable by the user. I don't know the exact number at the moment, but it's basically the number of queued up jobs at the Kubernetes scheduler and the amount of time that this job have been queued. These are the two main topics. But if you want further details, Xavier, you can send me an email and I can provide you with more detailed information about that.
Okay.
Thank you.
Okay, so I think we are perfectly on time. Thank you, Germán, for your presentation and all the assistants for the questions as well. So this is the last webinar before the summer break. Discover us now. Take a break for the webinars in July and August. We will host the next webinar September the 10th at 4 p.m. European time. Will be a webinar from Giancarlo Fortino. So you are, of course, very welcome to join us. So thank you, Germán. Thank you again. Thank you all for joining us.
Thank you very much for your attention. Thank you. Have a good day. Bye.
Bye-bye, guys.